In this video, we're going to continue looking at integrals which involve the use of partial fractions. With these examples, we have denominators which contain repeated linear factors. So here in our first example, we have x plus 9 divided by x over x minus 3 squared. And so this bit is going to be our repeated linear factor. We have a repeated factor of x minus 3 and it's repeated twice. Okay, so how do we do a partial fraction decomposition for this? Well, we start off with our integrand, x plus 9 over x times x minus 3 squared. And that's going to be broken or decomposed into two fractions. One with the denominator x and the other with the denominator x minus 3 squared. And we know that the numerator has to have a degree less than the denominator. So in the first fraction, that means that the numerator has to be a constant, has to be degree 1. And in the second fraction, the numerator has to have a degree of 1. Okay, so that's going to be bx plus another constant, which I'm going to call d. And you'll see why I call it d in a moment. All right, now the usual thing would be that we make a common denominator between these two and then we equate our numerators from the left and right hand sides. However, because it's repeated linear factors in the denominator, we do something slightly different. And this is the only time that you'll have to do it. I'm only doing it like this just so you can see where this comes from, and then you can use the result that we're going to discover. Okay? What we're going to do is we're going to write the numerator of the second fraction in a slightly different way. We're going to write it as b times x minus 3. Now, obviously I can't do that for nothing. What would happen if I expanded that out? I'd get bx minus 3b. So I've introduced a minus 3b into the numerator, which means I have to compensate for that by introducing a plus 3b. And then I still have my plus d. And you can see that these two will cancel out and we'll get exactly what that is. Okay, but because we're trying to do something clever here, we write it in this form. Okay, over x minus 3 squared. The reason we write it in this form is because now we're going to split up our numerator. So we're going to actually get two fractions popping out from the second one. The first one will be b times x minus 3 over x minus 3 squared. And the second one will be 3b plus d over x minus 3 all squared. And the advantage of doing that is now that this part, x minus 3, that factor cancels with one of the x minus 3's in the denominator. And so when we simplify it, we get a over x plus b over x minus 3. And then what's the numerator in the third fraction? Well, it's 3b plus d. But that's just a constant, so we might as well call it c divided by x minus 3 all squared. And so what was the advantage of doing that? The advantage is now we only have constants in our numerators. We don't have any x terms. And that's going to make it very easy to integrate each of these fractions after we work out what a, b, and c are. So now the task is to work out what a, b, and c are. So what was this equal to? That was equal to x plus 9 over x times x minus 3 squared. Let's make a common denominator on the right hand side. Clearly our common denominator is going to be x into x minus 3 squared. Okay, so we'll get a times x minus 3 squared plus b times x minus 3 plus cx. Okay, and now we can equate our numerators. So we have x plus 9 is equal to a into x minus 3 all squared plus bx into x minus 3 plus cx. All right, and now we need to use the techniques that we've already learned about to help us find a, b, and c. Now the first thing that I can notice is that if I let x equal to 0, that's going to take out this term. It's going to make that equal to 0, so the whole thing will be 0. So b is eliminated, and it will take out this term, which makes c, or the c term, go to 0. So we're only left with a. So I'm going to say let x equal to 0. And what do we get on the left-hand side? Well, we get 0 plus 9, which is just 9. And on the right-hand side, we get a times 0 minus 3. Well, that's negative 3. And then when we square that, we get 9. Of course, we have our plus 0 and plus 0 here. And so therefore, a is going to be equal to 1. I've easily worked out one of my coefficients here, or one of my constants. Now what could we do? Well, we could let x equal to to positive 3. And why is that helpful? Because it turns this term into 0, and it turns that term into 0. And so we're only left with the c term. So when x is equal to 3, on the left-hand side we have 12 equals 0 plus 3 times c. And so therefore, c is going to be equal to 4. Okay, so we've worked out two of our constants fairly easily. Now we just need to work out what b is. And how would we do that? Well, I think we should look at the coefficient of x squared. Coefficient of x squared. On the left-hand side, well, the coefficient of x squared is 0 because there's no x squared term. Where do we get the coefficient of x squared on the right-hand side? Well, it would come from a times x squared, which we'd get if we expanded out that bracket. And so the coefficient there would just be a. Where else? Well, we can get it from b times x. And so the coefficient would just be b. And that's it. There's no other way to get x squared on the right-hand side. So b is equal to negative a. And since we already know what a is, that's equal to 1, b is equal to negative 1. Okay, so now we can write our integral in the following way. It's going to be a on x, so 1 on x, plus b on x minus 3, which is negative 1 on x minus 3, plus c, which is 4 on x minus 3 all squared. Okay, well, we can actually integrate 1 on x, that's just log x. We can also integrate the second one. That'll be minus log of x minus 3. The third one, quite easy, but let's just write it in a different way. Let's write it as x minus 3 to the negative 2 power. And we know how to do powers of linear functions. It's just the same, it's just really the same as the normal power rule. So we add 1 to the power, which would make it negative 1, and then we divide by the new power, times the inside derivative, which is 1. Okay, and then we have plus c. What we might do, we might join these two logs together using our log laws, so that gives us x over x minus 3 minus 4 divided by x minus 3, just bringing it back down into the denominator. And then plus c, and that is our final answer. So this is a really important fact that you need to take note of when doing partial fraction decompositions where the denominator contains a repeated linear factor. So if the denominator of a rational function consists of a repeated factor, x minus alpha to the power n, then it can be resolved or decomposed in the following way. So we have our rational function, and it's going to be equal to a sum of fractions. And you can see that each time we have our repeated factor in the denominator, but it's increasing in its power. So we start with a power of 1, then a power of 2, and then 3, and so on, all the way up to the power n, whatever the amount of repetition it is in our original function. And the other important thing to note is that the numerator is always just a constant. So we have c1, c2, c3, all the way up to cn, and that's always just a constant. And that's what's really beneficial about this, is that we don't have to deal with linear numerators or even quadratic numerators. It's always just a constant. So our second example is looking at the integral of 2x plus 1 over x squared minus 1 times x plus 1. So before we do a partial fraction decomposition here, what we need to have our denominator completely factored. So if we look at our denominator, let's write it. 2x plus 1 over x squared minus 1, x plus 1. Let's try to completely factorize our denominator here. Well, the difference of squares, we can split that up as x minus 1, x plus 1, but then we still have that other x plus 1 sitting on the edge here. And so now we can see that we actually have a repeated linear factor. So we have x minus 1 times x plus 1 all squared. So we do have a repeated linear factor right here. So that means when we do our partial fraction decomposition, this is going to be a over x minus 1 plus b over x plus 1 plus c over x plus 1 squared. So we're using that fact where we build up the power of x plus 1 in the denominator in two separate fractions. Okay, so now we need to make a common denominator. So the common denominator will be x minus 1 times x plus 1 all squared. So we need a over, or a times x plus 1 squared, plus b times x minus 1 x plus 1, plus c times x minus 1. Now that's going to be the numerator of our fraction. Now we can compare that numerator to the numerator of the left-hand side, which is 2x plus 1. So now our job is to find a, b, and c. Okay, so where do we start? Well, I recommend starting with a few substitutions. Probably the most obvious substitution to make is when x is equal to 1. So when x equals 1, what do we have? On the left-hand side, we have 2 times 1 plus 1, which is going to be 3. And on the right-hand side, well, we have a times 2 squared, and then the b and c terms both have a factor of x minus 1, and when we sub in x equal to 1, that becomes 0. So we have plus 0 plus 0. So that means a is equal to 3 on 4. Okay, we can also find one of our constants by subbing x equals negative 1 in. On the left-hand side, we have negative 2 plus 1, which is negative 1. On the right-hand side, the a term will become 0, the b term will become 0, so we have 0 plus 0, and then the c term is going to be c times negative 2, which means that c is going to be 1/2. Now to work out the b constant, well, we can have a look at the coefficient of x squared. On the left-hand side, there is no x squared, so the coefficient is 0. On the right-hand side, where do we get an x squared from? Well, we get an x squared from a times the x squared that comes when we expand that bracket. So that'll be a times 1, which means we have a coefficient of just a. And we also get an x squared from b times x, which will be b times 1 as the coefficient, so plus b. So that means b is equal to negative a, and since a is 3/4, b is negative 3/4. And so what's our integral? Our integral is now a over x minus 1, well, a is 3/4, so 3/4 on x minus 1, plus b, which is negative 3 on 4, so negative 3 on 4 over x plus 1, plus c, which is 1/2, over x plus 1 all squared, dx. Okay, first two integrals are pretty easy to do. They're going to be 3/4 log of x minus 1 minus 3/4 log of x plus 1. The third fraction, let's just do it a little bit slower. Let's write it as x plus 1 to the negative 2, not negative half, negative 2. And now since that's a linear power, or a linear function, linear polynomial we should say, linear polynomial to some power, we can straight integrate that. But with these first two logs, since they have the same coefficient, we might as well join them together. So that'll be 3/4 log of x minus 1 over x plus 1 plus 1/2 x plus 1 to the negative 1 divided by negative 1 times the inside derivative, which is 1, plus c, and just to be neat, we can write this last bit as a fraction. So this is actually going to turn out to be a minus a half times 1 over x plus 1 plus c. And that is our final answer.